Find the derivative of x squared plus 1 to the power cosine 2x. And there's a lot of stuff here, so I'm not going to read through them one by one. But all right, we have a problem here. Now, before we get to talking about the answer, let's talk about the tool. What's the right tool to use? And how do we know? Okay, someone said natural log. In particular, there's no natural log here, so what does that mean? Log is correct. It's tied into it. What's the name of the technique? Logarithmic differentiation. Why do we know we have to do logarithmic differentiation? Not that like, well, I guess I'll do it. You don't have a choice. You're forced. What about this says you are forced to do logarithmic differentiation? Yeah, see how there's a variable upstairs and downstairs. If there's a variable both upstairs and downstairs, no choice. You are forced. You must be doing logarithmic differentiation. All right, so we know we're going to be doing logarithmic differentiation. We know we have formulas for that. We have ways of making this work. So what's the right answer? A, B, C, D, or E? Now, if it helps, you can narrow it down to 2 pretty much automatically. So let's write down the formula. The derivative of f of x is f of x times the derivative of the natural log of f of x. So, that's logarithmic differentiation as a formula, which says what? Our answer better include what we started with. Which options include what we started with? D and E. So you can toss out A, B, C. So now instead of a 1 and 5, you have a 1 and 2. Okay. Is it D or is it E? It is D. All right. So, as we've said, there's functions both up and down. You have to use logarithmic differentiation. Now, I will say there are sort of 2 schools of thought. There's the simple, here's this formula, remember this formula, and life is good. And then the other way. Now, the other way is what you may have been taught. So, what's the other way? Well, the alternate. And it works okay in some cases, and there's issues with it. The alternate is to say, well, set y equal to your function, and then take the log of both sides. Log y equals, I'm going to use properties of log, the cosine is going to come down, log x squared plus 1. And then what would happen? That's right, we would silently meditate and reflect on our choices that led us to this class. What did we do to have so much fun in Calc 1? So the idea here is now we're going to do implicit differentiation. So this is the other option. So you get 1 over y, y prime equals all this other fun stuff. And then how do you finish up? Well, you finish it up by saying, hey, I now multiply the y across and I replace what y is. So that's the other approach. There are reasons to prefer this approach, but you'll get full credit either way. So this is we'll call it the formula approach. This is the implicit differentiation approach. All right, well that was good. That was last time. Any other questions about this technique in general, I will say they love asking questions about implicit differentiation. Very popular. Very popular. And given that we're going to have 10 questions, it's going to show up. So make sure you know how to do it. All right. Thought for the day. Well, today's thought. You can't have too much of a good thing. And this also applies to studying. It's true, studying is wonderful. We want you to do it. But there's limitations. And oftentimes what happens, you say, okay, how effective is studying? Well, let's suppose we look at time. You get the most out of studying at the very beginning. A little bit of study helps. And then, over time, it starts to level off. And then it actually starts to go downhill a bit. So the thing is that if you want to get the most out of studying, what should you do? Well, one thing is, break your studying sessions up into small pieces. When you're doing small bits, you're getting the most efficient parts of the studying. That's why we say, don't study 4 hours once a week. Study a half hour six times a week. Even though it's less total time, you're going to get more effective time. Also, don't do long sessions because you start to get to the point where you're getting burnout. You've studied too much. And so one of the things is don't cram. When you start getting ready for those exams, you don't get ready for the exam on Wednesday night if the exam is Thursday. You start getting ready maybe the weekend before. Let's say after the football game. We'll assume Iowa State keeps winning. Probably won't, but let's say they do. We have to have dreams. We have to be optimists. After the football game, start your study. And so get the most out of it. Now, another thing is a lot of people think it's always about quantity. It's like, oh, I didn't do well. That means I just have to study more. But it's not. It's not about quantity only. It's also about quality. Are you having good study or bad study? You have to think about that. Are you actively engaged in your studying, or are you just passive? Are you listening to a lecture to help you fall asleep? I have lots of videos to do that. Or are you writing things down? Are you trying problems? Are you fighting your math? And there's a saying, you learn math by fighting with it. You have to work at it. You have to be actively engaged. And think about what is it you're doing? Why are you doing it? Work with people. If you don't have people, work with your duck. Talk to the duck. And so get the most out of your study. All right. So anyways, that's our thought for today. All right. Now, today is a wonderful day. Wonderful day. Let's start with the following. We're going to be talking about inverse functions again, but in particular, inverse trigonometric functions. So it's time we have the talk. When a mathematician loves a function very, very much. No. But I will say, you will notice there's a definite bias to arctangent. And I think that's in part because of me at Iowa State. So arctangent is it'll keep showing up over and over and over again. And one of the reasons why is we're about to talk about its derivative. It's a beautiful function, so let's talk about where it comes from. So here we have y equals tangent of x, and it's this periodic function. Now, tangent of x, is it an invertible function? And why not? So there's two parts to that question. Is it an invertible function? No, good. It's not an invertible function. Why not? Yeah, there's this thing called the horizontal line test. You can only hit it once. So what we do is we say, well, we want to talk about the inverse of the tangent function. So what we're going to do is just say, look, limit yourself to just sort of one copy of it. So we're going to go from the copy that happens to have vertical asymptotes at negative pi over 2 and positive pi over 2. We're going to take that, flip it across the line y equals x, and we have arctangent. Sometimes this is denoted tan negative 1 of x. However, I strongly encourage you to think arctangent, because there's this really bad notation that happens with trig. What is sine squared of x? Well, that's sine of x squared. That's what we mean. What is sine inverse of x? It is not sine of x to the minus 1. It's the inverse function. So there's this bad notation. We know it's bad. We've known about it for hundreds of years. But we're just so stubborn that we never fix it. So use arctangent. All right. What happened to these vertical asymptotes? What do they become? Horizontal asymptotes. So one reason arctangent is so cool is you have these nice horizontal asymptotes as you head off towards infinity or minus infinity. So it's a nice bounded function. That's nice. What are some other things? It's always going up, always increasing. There's some values that we know. They show up frequently. What's arctangent of 0? 0. Now, how do you find arctangent of 0? You flip the question and say, well, if I want to find what is arctangent of 0, that's the same thing as asking tangent of what angle gives me 0. And the answer is, well, if you plug 0 in to tangent, you get 0 out. What about arctangent of 1? Does that have a nice answer? Again, flip the question. If I'm thinking about inverse tangent, which is arctangent, and say, okay, well, tangent of what angle is 1? Do we know an angle that gives tangent of that angle being 1? Pi over 4. Right. So it has a nice value at 0, and it has a nice value at 1. And the hits keep coming. So, all right. But now, does it have a nice derivative? Oh, yeah. Oh, yeah. So, let's figure it out. Suppose y is arctangent of x. Now, we don't know how to take the derivative of arctangent. We're trying to figure that out. What do we know how to take the derivative of? That's related to arctangent. Tangent. So what we'll do is we'll say, well, that's the same thing as saying tangent of y is equal to x. So I'm applying tangent to both sides, and tangent and arctangent I think of as undoing each other. And now we'll take the derivative. So we're going to take the derivative of both sides with respect to x. Okay, should we do the left or the right first? We got to do both eventually, but which one do you want to do first? Left? Okay. What's the derivative of tangent? Secant squared. Now, is there anything else that we need? Y prime. Why do we need a y prime? Right. Because when we're doing implicit differentiation, we're thinking of y as being a function of x. We just don't know exactly what it is. Well, in this case, we do. It's arctangent. All right. How about the derivative of the right-hand side? What is that? It is the 1. Okay, so we're almost there. Y prime is 1 over secant squared y. And now you're like, cool. Not what we want, though. It's somewhat dissatisfying, so we're not going to stop here. What's our issue? Well, y prime is the derivative of arctangent. So that's fine. The problem is, I don't want to have an expression with the y. I want to get an expression with x. All right, so now we start thinking. We have secant squared y. X is tangent y. Is there anything that connects these together? Perhaps a nice formula. An identity, if you will.
Secant squared.
Secant squared. Okay, that's a good start.
The derivative of secant squared equals 1.
Well, not the derivative of secant squared equals 1. But there, think trig. Think back to your trig identities. All right, let's start with an oldie but a goodie. What's sine squared plus cosine squared? All right, you guys know that one quick. Let's divide everything by cosine squared. 1 over cosine squared. What's another name for that? Secant squared. Cosine squared over cosine squared. What's another name for that? 1. Sine squared over cosine squared. Tangent squared. Well, that's for x, but really it's any input. So here's the idea. 1 over secant squared y, for if I want secant squared y, that's like tangent squared y plus 1. But what's another name for tangent of y? Have we given tangent y another name? Oh yeah, tangent of y is x. So this is 1 over x squared plus 1. So the derivative of arctangent is beautiful. It's beautiful. It's beautiful. So, the derivative of arctangent, 1 over x squared plus 1, or 1 over 1 plus x squared. Now I can promise you that if you're going to get to the end of Calc 3, you will know this, because you were going to see this again and again and again. Of all the inverse trig functions, this is the important one. Even in places where like there's no way arctangent will show up. And then all of a sudden like, arctan! Ah! It's beautiful. All right, any questions? Okay, let's try some things. All right. So, we're going to do some practice of finding some terms. And let's just recall over here in the corner. We'll say the derivative with respect to, and I'll just use the symbol u, of arctangent of u is 1 over, and usually we say 1 plus u squared. All right. So, what's the derivative of natural log of 1 plus x squared? Do you remember how to take the derivative of a log? Yeah, there's an over thing happening with log. What goes downstairs? What's inside the function? Like, oh my gosh. What goes upstairs? It's 2x. Where's the 2x coming from? The derivative of 1 plus x squared. So, derivative of arctangent almost is the derivative of log of 1 plus x squared, but they differ. So there's a subtle difference. Okay, how about the derivative of arctangent of x squared? What would that be? Well, follow the rule. 1 over 1 plus something squared. What goes here? X squared. Whatever's on the inside, that goes there. Anything else? Times 2x. So this becomes 2x over 1 plus x squared squared is x to the 4th. All right. Any questions? Derivative of arctangent, sine of x. 1 over 1 plus something squared. What goes here? sine of x, because that's the inside. Take the derivative, plug the inside in. We're doing chain rule, function inside function. Anything else? Times the derivative of the inside, which is cosine. Now downstairs we have 1 plus sine squared. 1 plus sine squared, also known as 1 plus sine squared. Good. Yeah, it doesn't really simplify that much. So cosine x over 1 plus sine squared x. Okay, how about arctangent of square root of x? What do we have? All right, walk me through it. One over 1 plus square root of x squared, which will become x. Okay, anything else? So the square root of x, also known as x to the 1/2. The derivative of x to the 1/2. 1/2 x to the negative 1/2. Now if you wanted to, you can rewrite this. This x negative 1/2 goes downstairs, so it's like 2 square root of x, 1 plus x. All right, one more. Arctangent of e to the x. What do we have? 1 over 1 plus e to the x quantity squared. Anything else? Times e to the x. Now, how can you write e to the x quantity squared? E to the 2x. So if you have a power, power to a power, you multiply the powers together. All right. So we can take derivative of things with arctangent. All right. Any questions? Good. Then I have a question. So, for t greater than or equal to 0, a particle's position is given by a function, namely the function arctangent of t squared. At what time t is the acceleration of the particle 0?
1/3 of the quad root, or quad root 1/3.
Oh, the 4th root of a third. Nice. All right. So, acceleration, second derivative. Because you start with position, so you got to get the second derivative. And we say, all right, well, we just took the first derivative just a few minutes ago. That's not too bad. So now to take the second derivative, practice our quotient rule. We got to know all the rules, clean it up. If we want the second derivative to be 0, that means you want the top to be 0. And there's just a single t, solve for t. And there we go. All right. Cool. Okay, so a few more functions we do have to talk about. I do not have the same feelings about arcsine that I do about arctangent. So I will always sort of, when I hear an arctangent, my heart will skip a beat. Arcsine's like, eh. So what's happening? Same thing that we had with tangent. You have to take a part of the sine function. You can't take the whole thing. And so the part that you take is this piece here. And it runs from negative pi over 2 to positive pi over 2, which says that the highest value of 1 happens at pi over 2, and the lowest value for arcsine, it's at negative pi over 2. All right. Well, same process though. Same process. We'll start. We say, well, if y equals arcsine of x, it must be the case that x equals sine of y. Take the derivative of both sides. Derivative of x, 1. Derivative of sine, cosine. And y prime. So y prime is 1 over cosine. But not quite satisfying enough. The problem is we don't want in terms of y, we want in terms of x. So is there anything that relates cosine, which is what we have here, and sine, which is what x is? Anything at all? It's perhaps something we may have mentioned a few minutes ago, if that helps. Sorry, what? Yeah, you know it. Our favorite, sine squared plus cosine squared is 1. So sine squared of y is x squared. So cosine squared y is 1 minus x squared. So how do you get to cosine of y? Take the square root. So cosine of y is the square root. 1 minus x squared. Now, at this point in time, you're probably saying, oh, Steve, you goofed. You forgot something. What did I forget? Well, we'll get there. But this step, what's missing? Or what do we normally put in? Plus or minus, right? So you're looking at me and saying, hold on, wait, slow down there, Steve. You need a plus minus. Or do I? Dun, dun, dun. I do not. Okay, why not? This is a technical detail, but math is full of technical details. Where does the sign come from arcsine? It's this part from negative pi halves to positive pi halves. What's true about cosine if you're between, what's true about cosine if you're between negative pi halves and positive pi halves? The cosine function looks like that. So from negative pi halves to positive pi halves, cosine is greater than or equal to 0. So that's why we only need the plus. All right, so to finish it up, you replace cosine by 1 over the square root of 1 minus x squared. So the punchline, the derivative of arcsine of x is 1 over the square root of 1 minus x squared. And there we go. All right. We have asked questions about arcsin in the past. I won't say that we haven't, because we have. So you should know it enough to get through the exam. I usually just say I can rederive it on the fly. It only takes a few steps to rederive it, because I know the process. Long term, no arctangent. Short term, you should also know an arcsin, but don't worry about it for long term. All right, questions about arcsin? Good. Well, any other functions we should mention? Arcsecant. Good. Someone looked at the handout. Okay, so you have arcsecant, and now again we have the issue. It doesn't pass that horizontal line test. So we can't do just a piece like that. We're going to sort of do a half and half. So that's the part of secant that we're going to grab. So our arcsecant has this sort of curious shape to it. All right, well, this asymptote here, this is at pi halves, because that's at pi halves. Up here, this is at plus 1. This is at minus 1, and this is at pi, in case you wanted to know all these values, but generally speaking, we don't worry too much about it. All right, so we run the process. Here we go. We're probably pretty good at it now. We've done it twice before. Y equals arcsecant of x. X equals secant of y. Take your derivatives. What's the derivative of x? 1. Yeah, it hasn't changed much in the last few minutes. What's the derivative of secant? secant tangent. Anything else? Y prime. Chain rule. All right, now, good news. We know things. What are things that we know? What is secant of y? X. Cool. So you already have the secant part down. Well, but that's not the only thing there. So that's going to be a bother. All right. How do we handle the tangent of y? Well, is there anything that connects secant and tangent together? Something that we talked about a few minutes ago. Tangent squared plus 1 equals secant squared. But secant squared becomes x squared. So tangent squared y is equal to x squared minus 1. So tangent of y is square root of x squared minus 1. Now we get into the part. Here's the part. Technically this is a plus or minus, and I'm going to talk about what happens. So I'll write down the formula and explain what's going on. For now, if we focus on just this part, just this branch, then we're in the range between 0 to pi halves for the secant function. Tangent is also positive, so on this side, it would just be the plus square root of x squared plus 1. So on this right-hand side, we get that 1 equals x square root x squared minus 1 times y prime. Or, rewriting this, y prime is the derivative of arcsecant, and it is 1 over x square root x squared minus 1. All right, so that's the part of arcsecant we almost always use. There is a part of arcsecant over here. So this formula does not quite work, but it's really close. Oh, so very close. So we can fix it. The only issue is the sign. Look at the curve here. What is it doing? It's going up. What does that tell you about a derivative? Should be positive. Going up should have positive derivative. We're going to have a long discussion about that in the near future. But if I plug in a negative value for x, I'll have a negative expression on this side. So this is true for the right-hand side. To make it true for all pieces, you toss an absolute value in. And this is true for the whole thing. It's a very fine technicality, not one which you should have to worry about, but I don't want to lie to you. I'll tell you the truth. All right, let's try this out. Here we go. Find the derivative of tangent of arcsecant of x. And this problem is so nice. Let's see if we can't do it twice. Okay, so what rule do we need to do to take the derivative of tangent of arcsecant? Chain rule. All right. So what's the derivative of the outside? Derivative of tangent. Secant squared of arcsecant of x. Okay. Times, what else do we need? Derivative of the inside. So I'll just emphasize what's going on here. The derivative of arcsecant of x. All right. Well, this piece, secant squared of arcsecant of x, that's really secant of arcsecant of x squared. We'll come back to that. Do we know the derivative of arcsecant of x? Yes. So 1 over, we'll just assume the positive part. 1 over x square root x squared minus 1. What about this piece? Secant, arcsecant of x. What is that? Secant of arcsecant. What's going on? They undo each other. So what do you end up with? Well, they undo each other, so you end up with what you started with. So if you started with x, took the arcsecant, then took secant again, you should get back x. So this part is x squared. So you have x squared times this 1 over x, square root of x squared minus 1, so we end up with x over the square root of x squared minus 1. All right. So where did what? Where did this x go?
No, never mind, I got it.
Okay, all right, you got it, great. But just in case anybody else was wondering, there's an x squared upstairs, 1x down, 2x's up, so it's left with 1x down. All right, cool. Now, that was one way to do it, but let's do it another way. Why not? We have a few minutes, might as well enjoy ourselves. So, when we look at this expression, tangent of arcsecant of x, what kind of thing is arcsecant? What comes out of the arcsecant function? Like what object is it? Is what? It's an angle. So this is an angle. We're like, oh. Okay, so let's give it an angle name. Greeks loved angles, so we'll call it theta. So in particular, arcsecant of x equals theta, or secant of theta is equal to x. So we draw a triangle. Now, secant of theta, maybe we're not very familiar with that, but it's not far away from something that we are comfortable with. What is it related to? Cosine. Secant is 1 over cosine. So this is the same thing as saying cosine of theta is what? 1 over x. Now, channel your inner SOHCAHTOA. What is cosine? Adjacent over hypotenuse. Right triangle. Pythagorean theorem. Missing side, what will that be? There's a square root, spoiler alert. It'll be the square root of x squared minus 1. Have you seen the square root of x squared minus 1 somewhere before? Coincidence? No. There's a reason. All right. Now, what are we interested in? We're interested in tangent of arcsecant. Well, that's tangent of theta. How do you find tangent of theta? Again, SOHCAHTOA yourself. Opposite over adjacent. So, you say, oh, this derivative that we were talking about, instead of thinking of it as tangent of arcsecant of x, we can think of it as the derivative of the square root of x squared minus 1. And to make it calculus friendly, x squared minus 1 to the half power. All right, now we start going. Let's take our derivative. Okay, what do we do? What do we start writing down? One half comes down. X squared minus 1 to what power? Negative 1 half. Anything else? Derivative of the inside, which is 2x. The half and the 2 cancel. We're left with x upstairs. What's downstairs? Square root of x squared minus 1. The same. Well, yeah, because we're taking the derivative of the same thing. We're just writing it in two very different ways. All right. Any questions? Well, that leaves us a couple of minutes. So let's have you try a problem. Find f prime of 2, where f of x is 4 log x squared plus 1 minus arctangent of x. We have a couple of options here. 1, 2, 3, 4, 5. C? 3? Good. C. So no surprises here. Take our derivatives that we know, plug it in. Life is good. All right, that's it for today. See you on Monday.